Okay, so welcome everyone to those of you who survived my previous two lectures. So I hope you sustain this also. So let's go back to our original problem of bandits and let's shift the gears, not too much but little bit. Okay. So now I am going into the domain of adversarial bandit setup. So in the adversarial bandit setup, remember the setup, you still have the bandit setup, but the rewards of the arms are not coming stochastically, but they are generated adversarially by some algorithms. Okay, and the goal will be similar. You want to basically design the algorithm which are giving some regret guarantees. So here we will define what do I mean by the regret guarantees, and then we will continue. Okay. Okay. So again quick recap, we have n arms. Okay. At each time step t, the algorithm selects. So now we will, earlier in the last first class itself we saw that the deterministic algorithm ideally will not work, because no matter what you do it will place the loss of, it can always place the loss or the reward of 0 there, and then it will. So instead of the deterministic algorithm, now we will basically be focusing on some probabilistic algorithm, and this probabilistic distribution Pt over n action. So Pt, the notation that I will be using is the following, and I hope I am consistent with my notations. So I have n arms, okay, and at time t I represent Pt, which basically denote the probability distribution over n arms, okay, and within Pt I will basically denote Pit, which represent probability of pulling arm I at time t, okay. And by the nature what I will have, if I sum over all the arms I is equals to 1 to n, then Pit should be 1, okay. That is what I mean by the probability distribution, okay. And then what happens? So at any time t I select a distribution Pt, and after I select the distribution Pt, the adversary select the loss factor, okay. So what it does, to each arm I, it associate a loss which is between 0 and 1 to the ith action at time t. Now whatever losses it is placing in the previous time, this there is no relation between, it could be arbitrary, okay. And then what we are interested in is, in this setup generally, because it is adversarial setup, we move from the reward setup to the loss setup, okay. So now the idea is to basically minimize the total loss over a period of time, because we are selecting the arms with certain probability, we are interested in minimizing the expected loss, which is nothing but, so capital H denotes the algorithm that I am taking. At time t is nothing but summation over I equals to 1 to n Pit Lit. This is easy. Is this okay? Okay. So this is the Lit loss I incur for arm I with, because I am pulling that arm with probability Pit, this is the expected loss that I will incur. So far so good. Okay. Now this fact we have already established that no deterministic mechanism will work here, because whatever arm I choose, the adversary can always pull the things, but we will see more concrete example, because as mentioned by Pallavi in the morning that you can always put 0, right. So we will still have to worry about those cases, but at least intuitively I understand that the deterministic algorithm will not work. So when I say deterministic in this setup, what does it mean? It means that this Pit will be 1 for one arm and 0 for everything else. So that is what I mean by the deterministic algorithm. Sure? Good. Perfect. Okay. So yes.
Why is the adversary choosing the loss after it sees what the algorithm is doing?
Because you want the, so it's like this, right? So when you are giving the guarantees that your algorithm is performing best under any possible condition, in any possible condition, adversary, so by the nature of adversary, it is trying to, it's a very strong adversary.
But then,
But even if nahi, so for example, you can think about this, okay? Let's say forget about this setting, okay? Even like any kind of algorithm complexity analysis which you do, what you do, you basically give a algorithm and you do its analysis with respect to every possible instance. Worst case analysis, right? So when you talk about, even if you think about this kind of definition, then also here what you are doing, at every time you are selecting some PIT, okay, and then what you want to give analysis, you want to give analysis with respect to every possible instance. Now in every possible instance, I can basically create every possible instance, right? So that way also it matches. So what you will do, you will basically, you have some forget the algorithm, you have, let's say, t time steps and you have 3 arms. So at every time step, and let's say you want to put 1 on one thing and others 0, let's say you are only worried about 1 0 0. So at every time step you have like 1 0 0 0 1 0 0 0 1 3 thing. So you have 30 possible combination, right? So now in these, like you basically choose 10 combination out of these 30 combinations. So you basically choose all possible instances, and out of those instances you see your algorithm is performing worst again which instance, okay, and that would be the worst case performance, okay. So I'm saying it's similar to that.
Okay, so then can't I imagine that the adversary's behavior, this loss vector will always be, you look at the probability distribution along an algorithm has chosen, and it literally dumps the lowest
Yes,
on the probability, the highest probability case.
we have to, because this is the worst possible thing. Yes, yes, and we are interested in how best you can do even in this worst case scenario.
Right, so what can an algorithm do?
We'll see that. We'll see that. Yeah, yes.
What is the bound on this loss vector that the adversary can give? Like, it can give 1 to every possibility, and
we will see that. Once you understand what is meant by the best algorithm, you will understand the setup much better. Okay, just give me 1 or 2 more slides time. Anything else? Perfect. Okay, so what I want is some kind of best algorithm, and I understand you guys have too much doubts in this. So let's jump into it. How do you define the loss of best algorithm? Okay, so now what I am doing is basically, we do understand key when we are talking about every possible combination, we cannot hope to achieve better. So what we do is, what we define is some kind of algorithmic class. Okay. So what I am assuming is that the algorithm that I am choosing, which it will come from some class of family G, and then what will happen, the most general family of algorithm is to consider all possible functions. Okay. So what does it mean? It means that wherever, so when I say f from 1 to, sorry, this should be n, 1 2 dash dash, sorry, 1 2 dash 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 capital T, this is correct. This means that at any time 1, I can basically choose one of these. Okay, something like that. Okay, so this is possible thing, and what I am trying to do is, I am trying to find the answer to the question is that, does there exist a best learning algorithm H that gives the best regret guarantees. So now, because I have fixed my capital G, I can talk about, because I have fixed my search space which is capital G, I can talk about what is the best algorithm here it will do. Okay. So for every possible losses, whatever losses you get, you basically find an algorithm which would have done the best there, similar to our ith wala thing, right. So you are finding the algorithm which would have done best here, you are comparing your algorithm against that best algorithm. Okay. Let me repeat again. So what you are doing is, for a given instant you have all the loss vectors till capital T. With these loss vectors, once you have seen all the loss vectors, you are seeing which algorithm would have given me the best possible loss, that means the minimum loss after seeing all the losses. Okay. The algorithm which would have given you the best loss would be your minimum, and that you are comparing against. Okay.
So this is a hypothetical, this is an abstract concept.
This is an abstract concept.
I don't know what the algorithm is, but there is something that attains minimum loss.
Yes. So now let's go back to the previous questions that were asked. The first situation where the loss vectors that are generated, again for the sake of simplicity, because it is a new topic, I will assume that the losses are either 0 or 1. Okay. Now the first situation, let's say at any time whatever loss vector you get, the adversary is such that it is choosing at least loss of at least one action to be 0. Suppose it is not choosing everyone to be 1. Okay. At least loss vectors at each time are in such a way that at least one action gets a loss of 0. Okay. In that case, what will be LG min? LG min T, it will be
The algorithm which plays that arm.
the algorithm at each time which plays that arm which got the 0 loss. So in that case it will be 0. Does it make sense? However, if the algorithm is putting all the losses to be 1, coming back to Pallavi's question in the morning, if the algorithm is putting everything as 1, then the best algorithm will also incur a loss of capital T. Yes, then you are comparing against capital T. Okay. So your worst scenario is not when everything is bad, your worst scenario is when only one thing is good and others are bad, or maybe something else. But you understood this. Okay. Understood how we are comparing the things? Good. And in the most general setup, I am assuming my family of function or my family of algorithm could be anything arbitrarily. Okay. And this is a deterministic family. So basically at each time 1, I am choosing which arm to. So this is not probabilistically, this is deterministically. Okay.
Does H have to be part of G?
No, H is my online algorithm, capital G is the family of algorithm against which I am competing. I am finding the best possible thing. I will take half minute, you can just soak it in. Are we good? Perfect. Okay. Now, my first result says that even probabilistic algorithm, whatever you do, so what I am doing is I am coming up with the probabilistic online algorithm, and the algorithms which I am competing against are still deterministic. Okay, but they are very strong, that means with each time they may associate a different arm. Okay. If I go with respect to that, my first result is no matter what algorithm I choose, the regret, which is this, will be at least T into 1 minus 1 by n. No matter what algorithm I do, if I am sticking to comparison of any arbitrary function which can take this form, then I am going to incur a very huge regret. This is my first result. Any idea how will you get it?
The online algorithm is deterministic.
whatever you want. I mean, I don't have anything. So you choose whatever online algorithm. That's the beauty, right? So you give any online algorithm. Again, let's understand this question in a slightly different way. You give any online algorithm. This theorem means I can generate the sequence of losses in such a way that the regret will be at least this much.
So the adversary basically will see what the online algorithm is doing at any step and see if the thing that it does, the arm does not pick and puts most maximum.
Yes, so arm it does not pick, so that anyways is not going to work, but similar to this, because so then the question is, so what you are saying is arm it does not pick, give the loss of 1 to that and zeros to other, right? In that case the loss will be, the regret will be capital T. Do we understand this? We understand this, right? So if I am comparing against every possible thing, and if my online algorithm is a deterministic algorithm, then I will be choosing one particular arm at each time. The adversary will do what it will do, it will put loss of 1 to that arm that I am picking and zeros to everyone else. Okay. Now because zeros to everyone else, the best algorithm will always incur a regret of 0. The best algorithm will always incur a loss of 0. This we have already established. Ki at each time, even if one arm is getting a 0 loss, the best algorithm will be 0, will have the loss of 0, right? So the thing is that, now the thing is deterministic will have the regret of capital T, established, okay, but I don't want deterministic, I am happy with probabilistic, okay. But you extend the same thing in the probabilistic. Because your algorithm is probabilistic and because the sum has to be 1, there will exist at least one arm whose probability will be less than or equals to n, 1 by n. There will be at least one arm whose probability will be less than or equals to 1 by n. This is easy. If everybody is greater than 1 by n, then sum will be greater than 1. Okay. So at least one arm will be there whose probability will be less than or equals to 1 by n. Do we agree? We basically do the same logic. We put the loss of 1 there and zeros to everybody else. Nahi, ulta. We put the loss of 0 to that arm and 1 to everybody else. Okay. 0 to the arm which has the least probability, which is less than or equals to 1 by n. Okay. And then the other things, 1 to everybody else. Now what, at each time what is the probability that you would have not pulled the arm that has the least PIT but some other arm? 1 minus 1 by n. So with probability 1 minus 1 by n, you are incurring loss and t steps are there. So this is the regret that you get. Is it clear? Sure? Okay, good. More formally, this is the proof that I have written. So what you are doing, at time I, you find the arm which has the least PIT and assign 0 to that, everybody 1, and this would be your loss. Okay, good. So what does this tell you? See, we gave this very strong result, right? I am saying no matter what online algorithm you do, if you are comparing your regret against all possible family of algorithms, you are doomed. You cannot hope to get better than this. And this is easy to achieve anyways. Okay? So the question is, this is easy to achieve, right? How will you achieve this? Just uniformly pick, okay? Every time just pick uniformly, this is easy to achieve. There is nothing rocket science here, okay? And this is the best you can do. So we need to do something extra, okay? When you are stuck somewhere, what you do? In the earlier class we saw, we relax something, okay? Here what we considered is all possible class of algorithm is too ambitious, then what we do? We relax this. Do not consider all possible class of algorithm, restrict to something. but the problem is what restriction. Okay. Now again going back to the practical applications, okay, suppose you had this problem, okay. So this problem is basically, the prime example is, you know, let's assume you are basically, okay, any office. So you are taking a route from your home to your college. Let's say you stay outside the campus, okay. So you are taking a route from your home to the college, and then you have multiple routes that are possible from your house to the college, and the idea is you want to find the best route. Which route should you take to the college? Now obviously every time, even that particular route, one route will have different traffic condition, right. Today traffic condition will be different on the same route, tomorrow it will be different, and so on and so forth. It will be different, right. Still what you do is, what you do actually, you do not compare ki, you know, what should I take on Monday, what should I take on Tuesday, what matlab, you know, on this date I should take this path, on this date I should take this path. You do not do this. What you do? You basically see that what is the best route overall, you see what is the best route overall, and you take that route, okay. You do not do day wise distinction, okay. You just try to find the best route, and it is inspired by this. So instead of comparing with respect to all possible algorithms that are possible, you basically compare against the algorithm which is sticking to one best action. Okay. In the earlier stochastic also we are doing the same thing. We were basically finding which is the best action in expectation, and we want to find that action. Okay. Similarly, instead of optimizing against, instead of, you know, doing a war against all possible things, I basically stick to one person at a time. Okay. So one best action, and that is what I am going to compete against. Does it make sense? Good. So what I will do, instead of looking it to the entire class, I will restrict to the class which look for the best action, and in that case my regret is given as min over I LIT. Okay. So again do not get confused between this. So this minimum is outside this summation. So capital LIT is what? Capital LIT is, so capital LIT is what? Summation over I equals to 1 to n small LIT, total loss that arm I make, sorry. So my probability of making the mistake would have increased because of the tiredness. So please interrupt me if I am making too many mistakes. Okay. So LIT is basically the total loss that arm I is making till time capital T. This is what it is. And when I say min I over LIT, I am doing the summation first and then I am taking the minimum. Exactly. So what you will do, you will basically for each arm I, you will compute what is the total loss it has given, and you will choose the arm which has the minimum loss. Okay, do not interchange min and sum. Okay. So we understood this, okay, this is okay. Okay, and now what I want to do, I want to find the algorithm which minimizes this. This seems easy, I just want to see which action is best. So what do you do?
We want algorithm that will choose one of the arms.
You can design probabilistic also, does not matter. So we are not restricting ourselves to deterministic. We will start with deterministic, however, to gather the intuitions, but you are free to design deterministic or probabilistic. But the optimal against which you are comparing is just with respect to the one best optimal arm. Is it okay? So next question is, how will you solve this problem? if your math is I mean if you don't want to look into math, go back to the original problem of finding the best route from your home to your institute. How will you do it? Right. So, you will choose greedily. Every time you take some route, you note down the time it took you, and then the next time you would take the path which had given you the least time so far. Looks logical, right? That's what we will do in the first algorithm. Okay. So, what I will do at any time t, I would basically take the action which has given me the least loss so far. Okay. The only issue is it might happen that I may have multiple action which has the least loss. Okay. In that I will choose the one which has the minimum index. So, I basically number, so you basically number your paths, and then because you have not taken some of the paths, you do not know which one will give what thing. So, then you will take the path and try to see. Okay. So, algorithm is clear. So, algorithm is basically what one of you suggested. It will basically choose the action I which will have the minimum loss so far. Okay. If there are multiple arms with the minimum losses, then it will choose the arm which has the minimum index in that set. So, I am assuming there is an inherent indexing over the arms. So, arms are numbered 1, 2, 3, 4, 5 and so on and so forth. Make sense? Good. Okay. Hanji.
Why would the index matter? Why would choosing minimum?
Just I wanted to have something to break the ties. Okay. So, there are two arms with the same losses so far. Then how will you choose? I just said you fix an index and then just break the tie. This is deterministic. Definitely deterministic. No probability. Adversary will mess up with any algorithm, but still we are looking for the regret guarantees. It will, and you will see it does not have very good regret guarantees, but at least this is first step to build the things. Okay, but it will not be too bad as t into 1 minus 1 by n, because the comparison class we have restricted. We have restricted the comparison class. So far so good. Perfect. Okay, so what can we say about the regret guarantees? Any ideas? Let us try to see an example. Okay. Suppose I have 5 arms. Let us try to see what will be the regret with respect to 5 arms. Okay. In the first round, what will I do? I will choose arm number 1. Sorry. Somehow the silence is not. Okay. So, in the round number 1, I will choose the first arm. Okay. And what the adversary will do, because it need to so it need to give me the maximum loss at time t equals to 1, it will put a loss of 1 here and zeros to everything else. Okay. Then in the second round, what I will do? Choose 2, and then t equals to 2, this will happen. T equals to 3, this will happen. T equals to 4, this will happen. T equals to 5, this will happen, and you get the flow. Okay. But what I am interested, okay, it is written here, but what I am interested in, just to understand that one is on the same page, what will be the regret in this case? It will be, what is the best algorithm here? The best algorithm could be either choose arm number 2, 3, 4, 5. So, for all the arms except one, the total loss is how much? 5. Okay. Whereas 5 or 4? No, 1.
One for each of the.
One for each, right? So, for all the other arms 2, 3, 4, 5, the total loss is 1, whereas for arm number 1 it is 2. Okay. So, the best possible arm is either 2, 3 or 4 or 5, does not matter, you take 2. Okay. So, that is the loss of 1 that you incur for the optimal one. What is the loss that your algorithm has incurred? 6. You incurred a loss at every round, right. So, the regret is 4. 6 minus 1, 5. Sorry, 6 minus 1, 5. Okay. So, we understood it. ठीक है. But can we make general regret guarantees? Can we actually analyze this algorithm and give some guarantees?
You can put a bound
How will we put the bound?
less than or equal to 5. Less than or equal to 5.
No, this is just an example. I am talking about, capital T rounds and whatever n numbers. This is just an example to show you how the things are happening. Okay.
T minus 1, whatever we choose.
So we can be fooled by that person.
No, this is just an example. You need to basically take n number of arms and capital T number of rounds. It's not easy to, it won't be exactly T minus 1 or something like that, because it's round robin, it will be, because n is significantly less than capital T.
And this
Number of arms.
But truly,
Hmm.
the fact is, the greedy algorithm test will tell the adversary exactly where the algorithm is going to push.
Doesn't matter, you are basically competing against the fixed action.
What is that? Okay, this is conception I know this, I'm not following something. So the fact that the greedy strategy is well known, and it also specifies that in this sort of time step, what choice the algorithm will make. Greedy will always put maximum loss on that choice.
That is fine, but what I am saying is, even here, right, your regret was not 6.
T minus T by n.
It was a difference.
It was a difference, right. So, even though and another logic is, the greedy algorithm is always choosing the arm which has the least loss so far.
Correct.
Okay. So, now imagine an arm which has the least loss so far. Okay. And if you choose this arm, you might incur a loss there, that's perfectly fine. But if this would have been the optimal arm, then you are not actually incurring the regret on this.
Correct. But the adversary will ensure that this is not the optimum arm and time step T.
But then you would have chosen, then this was the optimal arm because
T
it,
minus 1.
exactly,
Oh, that one step the optimum does not shift too much.
yes,
T minus T by n.
something similar. Okay. So, what is happening is the following. Let's try to understand this. Okay. Now, let's try to understand when you incur a regret. Okay. Like we were discussing, you only incur a regret when you pull a suboptimal arm. Okay. So, now what you are trying to see is that you fix an optimal arm I, because this arm is fixed, right. And what is how much time that you will take to reach to this particular arm I. Okay. So, basically what you are saying is, at each time imagine the greedy algorithm has incurred a loss of 1. Okay. And if you are incurring a regret at that time, that means LT-min is not increasing. What does it mean? If you are incurring a loss of 1 and LT-min is not increasing, that means you are basically pulling a suboptimal arm. Okay. Okay. Because the LT-min is not increasing and you are incurring a loss, but then what will happen? Every time LT-min does not increase, at least you would have eliminated that action from your set. In this case, this is what is happening, right. If 2 is there, if you understood, right. If for example, action number 5 is the best optimal, okay, then what you are doing, maybe at time t equals to 1, you are pulling one arm, LT-min is 0, you have incurred a loss of 1, okay, but then you know you do not have to choose 1 now, okay.
Yeah, now it is 2, 3, 4, 1
Right, after those number of rounds you will basically incur a loss. So either of the two things will happen, either you incur a regret of 0 or LT min will increase by 1. Right. So same thing is happening at each time when your greedy algorithm is incurring a loss of 1, LT min and LT min is not increasing, that means you are removing at least one action from your ST. Okay. And what is the worst possible case? When you will have to repeat n action to do that, right. So this can occur at most n times before LT min increase by 1. So with every increase in LT min, you are incurring the regret of at most n. Okay. So you straight away get n into LT min. Okay. And this is just additional factor ki last time ke liye you might have to do n minus 1 more. Does it make sense? Perfect. Okay. This is bad still because n into LT min, something like that. I don't know bad or good, but the main question that we always ask, can you do better? We have the lower bounds, right? We should have something. So can we do better? The answer is unfortunately not. And when you want to do this, what do? You basically prove the lower bound. Okay. Now coming back to the earlier question, greedy algorithm is a deterministic algorithm. So the next theorem says that no matter what deterministic algorithm you take, the regret will be at least this much. Simple. Okay. If you prove that any deterministic algorithm will incur a regret of at least this much, then you are done. Okay. And this is the theorem. For every deterministic algorithm D, there exists a loss sequence for which what happens? Your deterministic algorithm incurs a loss of T, whereas your optimal algorithm incurs a regret of T by n. Okay. And this is easy. This is why you basically mention T minus T by n. Okay. How? So for every deterministic algorithm, you are doing the same thing. You are putting a loss of 1 to the arm that deterministic algorithm is pulling and 0 to everybody else. Yes. I don't know, it's on silent, still it's ringing. Okay. Where was I? Okay. So for every particular arm, what you are doing, whenever a deterministic algorithm is choosing an arm I, you are saying this has the loss of 1 and others has 0. Huh? So LDT will be T. But what will be the LT min? What could be the LT min? LT min is basically, LT min can go high. So what you are doing is, what you are trying to prove is that regret is at least this much, right. So LT min will be less than or equals to T by n. Why?
Because after each n rounds you would be adding 1 to the optimal.
So which one will be your optimal one? Your optimal one will be the one which would have got the least loss, right, the least loss. Okay. There will be at least one arm which would have gotten less than or equals to T by n pulls. Okay. And that arm would have not basically got the loss, right. That is your best arm, right, and the best arm ka loss will be less than or equals to T by n, because this arm has been pulled less than or equals to T by n rounds. Okay. So your regret will be T minus less than or equals to this. So regret will be greater than or equals to T minus T by n. Okay. You do this, you will get this. Okay. So what I am interested in is this particular term, that you cannot do better than n into LT min. This is easy. Is it okay? Sure? Okay, good. Okay, so deterministic algorithm has some issues. Now what we want to do, we will see whether probabilistic, can we do something probabilistically, right. So in order to devise the algorithm which work probabilistically, you need to first figure out what went wrong in deterministic.
Because adversary always determines after we determine R, so that is the problem. So
No, but adversary will always determine after you decide.
like
You cannot
if,
change the problem.
if we do probabilistically, so then also every time it will put a loss of 1 to R.
It can, right? No, no. So when you say probabilistically, the algorithm will put some losses, but it's not considering what arm you actually pulled. So for example, you have arm number 1 and arm number 2. With arm number 1 you gave the probability, let's say half, and arm number 2 you gave the probability half, okay, and the loss sequence that is generated by the adversary is arm number 1 gets a loss of 1 and 0 to arm number 2. Then your loss, then your expected loss will be half only.
After we have pulled an arm, the adversary is generating the loss of the right, but there it is generating almost simultaneously.
No, in this case I guess my language was different, but at least in the first slide when I told that I will basically select PT and then after that the adversary will select. So my language would have differed over the things, okay, but not pulling, but after selecting the PT distribution, okay. Thanks. Yeah, otherwise we are not going anywhere.
But this adversary is also adaptive. It can see my probability distribution.
Yes, definitely, it can see.
But it doesn't know what sample we actually take.
Yeah, our action precisely.
It just knows that this is the probability vector, you are sampling through the probability, but actual what you are taking is
Because
this.
there it knew that my probability was 1 and 0, so it always knew that I am going to put here. But now it is half and half, so he is also like he can't do better.
He can't do better than half, yes. Yes. So if it has to put at least 1 0, then the thing is that it is half only, right. So then I reduced it little bit. Okay. So what went wrong in the deterministic? The problem that happened was, if my ST, the size which contain the arms with the least losses is too big, okay, then I am basically selecting one arm and then second arm, the third arm, fourth arm, and so on and so forth. So it is basically taking too much time to reach to the optimal, right, and the adversary is making me loss every time, okay. So instead of that, the example which I gave you, if you associate a probability, if you have only two arms and you say half probability this, half probability this, then immediately you reduce your regret by half. Does it make sense? Okay. If you had two arms earlier, then you would have first selected one, then I would have incurred a loss of 1, and then 2, and then I would have realized, okay, second is the best arm or something like that, right. But now suppose instead of this I am doing first arm I will give the probability half and second arm I am giving the probability half. No matter which arm adversary put a loss of 1, 2, I have reduced my loss by half. Does it make sense? This is the idea for the next algorithm. So instead of deterministically choosing from ST, instead of breaking the ties by smallest index, you basically do a uniform sampling from all the ST set. Okay. So earlier you were incurring the loss of n. Now how much you will incur? So first time when you are choosing the wrong arm, what is the probability that you end up in choosing the wrong arm? So now you are so if you had k arms in your set, okay, then what is the probability that you end up in choosing the wrong arm? It would be 1 minus 1 by k. it would be 1 minus 1 by k. So, at least you reduced your loss by 1 by k, right. Earlier you were incurring the loss of 1, now that thing is reduced by 1 by k. So, now the loss is 1 minus 1 by k instead of 1. That is precisely the area, the idea. Okay. Okay. So, now what I will do is, this is called the randomized greedy algorithm. It is just a slight version of the greedy algorithm. What it does is, it basically instead of deterministically selecting the set, the arm from this ST minus 1, it assigns the probability. Okay. So, it assigns the probability, uniform probabilities to all the actions which have given me the least loss so far. Okay. And I won't go into the detail, maybe we can discuss later. Just this simple step brings down the regret from the factor of n to log n. And the proof is similar, you know what I told you. For every increase, you basically have a sequence that converges to log n. This is mota like rough idea about how proof goes. Okay. This is good. Okay. But the same thing, but the same question that I want to ask, can we do better? Okay. Can we do better? Yes, please.
In this case, we are once we choose the first element, then in the next round we are uniformly distributing the probability on the remaining k minus 1 elements.
No.
We are not choosing the first.
It depends, like if the first, so for example in this case, if I am choosing the first arm, and if let us say it would have incurred a regret of 0, loss of 0, let us assume, and the other arm would have incurred a loss of 1, then for the second round, my set of arms that have given me least arm will contain 1. I am basically seeing which of the arms have given me the least loss. That was my greedy anyways doing, but earlier in deterministic algorithm I was breaking. So, ideally I was supposed to choose an arm which has given me least loss so far. Okay. The greedy was breaking the tie, deterministically, picking the least index one. The randomized algorithm is basically assigning the probabilities. So, at t equals to 2, what it will do? It will basically pull the second arm with probability 1 by 4, third arm with probability 1 by 4, fourth arm with probability 1 by 4 and fifth arm with probability 1 by 4. So, even at t equals to 2, this is my loss, then also I am incurring this particular loss only with probability 1 by 4. Okay. And if the loss would have been 1, 1, 1, 0, then I would have incurred the loss with probability 1 by 4 plus 1 by 4 plus 1 by 4, 3 by 4. Okay, make sense? Good.
So we are decreasing the expected because we are moving from loss to expected loss, it decreases. But then what do we do with it? We'll ultimately get a profile instead of a deterministic way to basically play the game.
You get an algorithm, right? So, you got PT, at every time you are just sampling, you are just throwing a coin with that probability distribution and choosing the arm. It's just
What will the output be? The output will be a profile of like probability distribution.
Yes, the output will be the probability distribution, and in real world if you are implementing with that probability distribution, you will take the arm.
How? I have to
Just
determine
sample from that distribution.
Okay. But
That's how
then
you
that will ultimately become the deterministic thing, right? If I get the output as a probability profile and in the real world I am playing it using that output, I am again converting it back to the deterministic.
But adversary is choosing the loss after seeing only your probabilities, right?
Yes.
So, if it is choosing the loss after seeing your probabilities, then you will have to talk about the expected loss, because with a reasonable enough probability, you are not taking the worst arm.
Okay. So, right. So maybe I'll have games where it will be greater than the expected loss, but in
In expectation, this in expectation this would be okay.
Yeah, but
That's the definition of expectation. You will incur the more loss somewhere and less loss somewhere. Okay, anything else? Where was I? This was done, this was done. Okay, no, I haven't done this. Okay, so I still want to, so now I will just skip the proofs, okay, just focus on the intuitions, okay. So I am still not happy with this log n terms, okay, so I want to do something better, okay. In this algorithm, what is happening is, I am doing the greedily, but I am not, again intuitively I am not actually taking care of my past too much, right. So let us say at time t I have multiple arms which had incurred some loss, the minimum lost, okay. I am putting equal probabilities to those, okay. In weighted majority algorithm, what I do, I basically increase or decrease the weight gradually, okay. So what I do in the randomized weighted majority algorithm, initially I say that every arm is, this has happened in the randomized greedy algorithm also, because I do not know anything about the losses, everybody is equal, then I pull everybody with uniform probability, okay. Now in the randomized greedy algorithm, what would have happened is, if the ith arm incurs a loss of 1, then I would have simply assigned the probability of 0 here, an earlier algorithm, okay. In this algorithm, what I do, I do not just switch gear, I do not just assign the probability of 0 to this arm, but I reduces its weight, because it is incurring some loss. I basically say wi t minus 1 minus eta, reduce its weight, reduce the probability of choosing this arm by a factor eta. If eta is equals to 1, then this becomes similar to what I had, okay. And then what you do, this is the weight, because you will have to normalize it, you normalize it and then you get a new PIT, okay. So PIT is nothing but the normalize of these weights. So now what I am doing, I am starting with a weight, uniform weight to every arm, and whenever I am pulling an arm and it gives me a loss, I am reducing its weight gradually, and how much weight I reduce, it depends on the factor eta.
So eta will be same for everybody.
Eta is same for everybody, because analysis will become too complicated.
It might happen that it just moves every time it has very big or very small.
It can't, because it is always reducing, right. Eta is less than 1 by the way, you are just reducing, you are not increasing.
So if every round I choose each arm and each time I reduce the loss, like each time I lose by 1, then it will, all the probabilities will reset to uniform again. Because each arm I went through each arm went through loss, then probability
Will go back to uniform again, yes. Yes, because everybody would have reduced by 1 minus eta, it would have gone back to the uniform. So everybody would have reduced by exactly same amount, and then you would have gone to the uniform probabilities, yes.
Eta is constant. Then after the first weight has been decreased, then others weight with respect to the first one will be increased, because we are normalizing it now. So then when in the next iteration, when somebody else's weight is being decreased by eta, now it is a little bit lesser, because after normalization it had relatively increased.
Over the period of time, maybe it might become equal, but in the first itself,
because first iteration, because you are normalizing, but it is not with respect to, you are not WIT, okay. So WI is 1, so WIT for the arms that you are not pulling is not changing, only the one you are pulling is changing. So even whatever you are saying, even the probability is increasing, the WIs are same. So whatever he said is correct. After all the rounds, if everybody has incurred a loss of 1, then you will basically go back to everybody having the same weight. So, the analysis will be similar, that how much these weights are reducing, right. So, every time you make a loss, the weight will reduce, okay, and for the optimal arm where the weight is going, and then how you will compare the regret. Okay. Now, with respect to eta, what you can do is, I do not think I will have the time to do the proof.
Like multiplicative weight update.
Yes, it is multiplicative weight updates.
So you can.
It's exactly the same. Yes. So, the regret basically becomes 1 plus eta LT min plus log eta by n, and then what you do is you basically work with eta such that this right hand side equation become the least, okay, and if you set the right eta, then you can prove that this regret is basically 2 of the order square root t.
So I also had this on the second lecture. I then do not disturb us. It was on.
Yeah, I don't know. I have actually minimized the volume. I have made it on vibration mode. Nothing seems to be working.
It's okay.
Yeah.
How do we get this value like the intuition? Eta should satisfy this norm plus eta times.
So, what you are talking about, this particular regret, it's similar. So, when you basically see whenever you are incurring a loss in LT min, what is the weight that you are actually incurring, like how much increase in weight that you are getting.
The reduction in LT min is basically LT min was a minimum loss.
So basically initially if you start with, I don't know if I can explain it in a better way. So initially you start with the uniform weights, right. So initially since you started with the uniform weight, the maximum loss that you can, so whenever LT min is not increasing and you are incurring a loss, so that is basically only with probability 1 minus 1 by n, right. So you make that kind of an observation, but you would have also reduced the weight.
Right. So that's weight adjustment. But that weight adjustment only happens by a factor of 1 minus eta.
Yes. Yes.
So we basically see how many times your weight may have fallen.
Yes. I don't know. I will have to see. Let me look into it and then explain it better tomorrow. Okay. Okay. But this is good. You basically reach the regret of square root t, which is pretty good. And my final slide is basically connection, again a very small connection, and hopefully if the time permits tomorrow, once I have explained you the cooperative game theory, I will make the relation with respect to the n players also. So currently what I am interested in is understanding 2-player constant sum game. Okay, do we know this?
We did 2-player zero-sum game.
Okay,
Min-max theorem.
ठीक है. So you assume 2-player zero-sum game, and I am just worried about min-max theorem. It's okay if you know that. Okay, this is enough for me. So in 2-player constant sum game is basically the similar concept that you had in zero-sum game. Instead of 0 you have C, but let's assume it's 0. Okay, let's focus on 2-player zero-sum game. So you have u1 of s1 comma s2 plus u2 of s1 comma s2 equals to 0 for all s1 and for all s2. ठीक है? Okay. Now wherever it's written constant, read it 0. Okay. So we know that zero-sum game has a well-defined value v1 and v2. So for player 1 you will have a value, for player 2 v2 have a value. So what is the value? I have revised all the concepts today: auction theory, Dagwa, GS theorem. What is the value? Sorry.
The payoff.
Sorry? No, what is the value of a game in a 2-player zero-sum game? Have you heard this term?
You mean payoff?
The value of min max.
Value of min max, thank you. So its value of a game is the min max value, and because of the maximum theorem, min max is same as the max min. Okay. Okay. So now let's go back to the interesting stuff. Okay. Now game theory in practice, it's very nice, okay, but when you go to the practical setting, there are various things which do not fall because of the practical issues, right. So one of the major assumption that game theory makes for the 2-player zero sum game is that all the players know everything. Okay. So the players know the utility function, the players know the strategy space, the players know, so then they can decide what will be the rational behavior. Does it make sense? Go to the setting when the players do not know these valuations, they do not understand the game, and they can only gather the information of this game by taking the action and realizing the mistakes. And this is what happens in practicals, right. In practice, what do? You basically take an action and you realize this is what the loss you incur, can you take some other action? Okay. So now I am connecting the adversarial bandits with our game. Okay. Now in this particular scenario, 2-player zero sum game, you assume there are 2 players, the only thing is they do not understand the game that well. Okay. But let us assume they understand how to minimize the regret. Okay. So then what will they do? They will take an action, they will incur some loss, okay. They will realize they have made the mistake, and the next time they will take some other action. Okay. And the other person will also do the same thing. Okay. Does it make sense? Okay. In here what we are interested in is, we are interested to find when every person, every agent is taking a regret minimizing algorithm, okay, then over a period of time t, which equilibria do we reach? This is the question that we are interested in, okay, and that happens to the correlated equilibria, which we will do tomorrow. Okay. But before that, I have the last theorem of the class, which says that if I have a zero sum game with the value V1 and V2, okay, and if suppose there is a player which plays for t steps using an online algorithm ON, which incurs a regret of capital R, forget about external, it incurs a regret of capital R, then the average loss will be basically bounded by Vi plus R by T. What is Vi? Vi was the value of the ith player. Okay. So, what it is saying is that when t tends to infinity, then the average loss of the player will basically converge to its value, which is good. Then even if I do not know the things, if I basically take the regret minimizing algorithm, I am still okay, I am still in happy place. Okay. And how will you prove this? So, forget about these 2 lines, understand the intuition from the third line. Okay. So, first of all, there exists an action of, let us say for the sake of understanding or without loss of generality, it is the ith player that I am talking about is the player number 1, who is basically opting for the online thing. Okay. Now, because of this maximum theorem or the value, you know that for each and every probability distribution of the other player, okay, there exists a strategy of the first player such that it fetches him it, the utility, this should be loss somehow, sorry, the loss will be less than or equals to V1. This should be loss, not the utility, sorry, my mistake. So, the loss will be less than or equals to V1. Okay, we know that. Okay. Now, so whatever the best algorithm would have done, okay, the best algorithm would have done better than this. Okay. So, the best algorithm, the loss of the best algorithm will be less than or equals to the loss which the algorithm would have incurred if it would have taken the action k at each time. Okay. So, LT min will be less than or equals to LKT, which is less than or equals to V1T. Okay. So far so good. Okay. But if I talk about the online algorithm, okay, the online algorithm is doing what? Online algorithm, because it has a regret of R, the loss of the online algorithm will be less than or equals to the minimum loss plus the regret. Okay. You take the average, you get the result. Okay. Okay. So, another interesting fact is, which I am not covering because, so QJ is basically mapping the online wala thing to the probability distribution. So, it is basically trying to understand what the second person would be doing, like how do you make up this QJ here. Okay. So, it is basically considering, you consider the when you are incurring this V1T, when this probability distribution is basically coming for the player 2, right. So, you basically see on the action J how much probability it has kept for T rounds. It is just constructing this queue for the second player. Mixed strategy of player 2 who has nothing to do with the online algorithm. Yes. Okay. So, interestingly, what you can do is, you have seen the proof of min-max theorem. Okay. So, interestingly, what you can do is, you can also prove min-max theorem using this regret by assuming that there is a algorithm which gives you sublinear regret. Sublinear regret means R divided by T goes to 0. Okay. So, if you have a regret minimizing algorithm which gives you the sublinear regret, then you can prove that min-max, you can prove your min-max theorem if both the players are using the regret minimizing algorithm. The idea is essentially same, but yeah, that is what you can do. Okay. So, with this intuitions, I guess enough of this. So, with this intuition, let me end here, and if the time permits tomorrow, I will try to come back to it with respect to the correlated equilibria. Okay. If the time permits. Okay. That is all.
When we have this idea of constant sum game, then the fact that I know my utility function, the fact that it's a constant and it's a two-player constant sum game, I can immediately deduce what would be the utility
Of the second player. Yes.
Right? This is where the second player does not have to randomize. It can only respond. So, you said the first player is playing an online strategy. So, the second player knows that my outcomes will be maximized if I minimize this first player.
Perfect.
Rather in the language of regret, it should be this first player is trying to minimize its regret. Second player responds. Regret. So the second player can minimize its regret by maximizing the first player's regret. That's the same.
Yes, this is the same sort of a thing.
So, and you're saying that if I have an online algorithm which has bounded regret, then they back the min-max
Theorem.
theorem.
Yes.
Both of them have to play with their
Regret minimizing strategies. Yes. I mean, it's intuitively it makes sense, because eventually it will have to
be at a common point.
at a common point. Yes, because eventually R by T is going towards 0.